So this is a talk given by Matteo Zavatteri from the University of Verona, and the title is about mining significant temporal networks is polynomial.
Okay. Thanks for the introduction. Right. Can you hear me loud? Yeah.
Yes.
Good. This is a joint work with Professor Guido Sciavicco at University of Ferrara and Professor Tiziano Villa at my same university, University of Verona. So this is about mining temporal networks. And the outline and contribution of this work is mainly a polynomial time algorithm to mine a significant temporal networks. And the outline is really simple. I'm going to give you a background on the reference model that we employed, and then I'm going to discuss how the execution traces look like from which we want to mine a temporal network, then discuss the mining algorithm, and then draw conclusions and future work, and discuss future work. So let's start with the model that you have partially seen this morning in the keynote speech of Professor Eder. In temporal networks, there are many extensions. Some of them extend a bottom formalism of STN, simple temporal networks, which basically are directed weighted graphs. And when we extend, we add components, we add conditions, we add decisions, we add uncontrollable durations. So any component, every time that we try to extend a temporal network, we can reason on extending it with a controllable part or an uncontrollable part. So here there are many acronyms. So the top level one is a model that I developed during my PhD, and it's called Conditional Simple Temporal Networks with Uncertainty and Decisions. So in this lattice of formalism, whenever it appears in the acronym a red letter, it means that the formalism contains an uncontrollable part. Whenever it appears an extension involving a black letter, it means that that part is controllable. So with U, we basically highlight uncontrollable durations. So are the durations which a closed interval in which we can decide when to start them, but we cannot decide when to end them. We have the guarantee that the relative temporal distance between these two time points, which are the continuous variable of the problem, fall inside the specified intervals. After that, we have temporal constraints, which may involve a numeric part. Typically, when the number is positive, it is a deadline, and when the number is negative, it is a delay. We might label them with conditions and decisions. So each condition or each decision is abstracted away as a Boolean variable, which is associated to a time point. The semantics here, it means that there are special time points which can be thought of as being discovering time point for either deciding something, so for making some decisions which is beyond the temporal part, or observing some conditions. Whenever we have a Boolean variable which is red, we execute, when we execute the corresponding observation time point, we are told about the truth value. This is the main difference. Whenever we execute a decision time point, we decide the truth value. And of course, our goal is that of satisfying all constraints which are coherent with the set of literals that appears in the labels. So these traditionally, in temporal networks, you can see labels as conjunctions of literals, so there is no loss of generality in considering sets of literals. So this is the model from which we want to start, and the goal is to try to mine a significant CSTNUD. So a starting point for this problem was that of defining execution traces. So execution traces in this context are a finite sequence of statements, where each statement can be of 6 forms, even if the last 4 are pretty much the same with some slight difference. So first statement, for example, it means that we have a controllable time point, something that we can control that has been executed at an absolute time A, happened at TA during the past and whenever that process was executed. Or we have the execution of a contingent time point. A contingent time point which refers to the corresponding activation at some specific time. Or we can see that some decision was made true for this Boolean variable or false for the same Boolean variables, and the last one are the same of these two, but with conditions. So this is an observation, and we get to know that A was assigned true or was assigned false. So an example of trace is this one in which we have time point Z, which is can be thought as a 0 time point when the process started actually. After that, we see that we executed a controllable time point A, and note that besides these 2 time points were executed at the same time. There is also an ordering among the execution. If someone of you is interested, there are problems in temporal networks in which the order plays a crucial role. So it is not only a problem of before and after, but it is also the problem of what happens at the same time. After that, we observe that the associated Boolean variable has been assigned true and stuff like that, until we discover that we also have a contingent time point which refers to the activation A. So as a reasonability assumption, we assume that traces were well defined. It means that they don't contain nonsense. So any time that we either have an observation time point or a decision time point, the Boolean variable which is connected to that time point appears immediately after. Likewise, for contingent time points, they of course have to appear after the corresponding activation. And traces must also be coherent. So it means that if we are given a set of traces, the components of any pair of 2 traces must be coherent with each other. So it means that we cannot have a trace in which we have an uncontrollable Boolean and another one in which we say that the same Boolean is under control, or a time point is contingent and not contingent in the other trace. Traces, however, might also be partial. So we can also start from mining partial information. So we did not assume that the traces must contain all the events of the process that we are trying to reconstruct. And the final goal was that of trying to understand what we can do with mining and uncontrollable parts. So can we mine a network which is eventually controllable after mining? And it was and it still is a strong challenge. So at the moment, as a starting point, we went for mining a significant temporal network. So this led us to define significance in temporal networks, which basically is a simple concept. It means that a temporal network is significant for a trace if it contains in a coherent way all the parts or the time points and all the Boolean variables that appears in the trace. And also significance means that if you take a trace and you substitute the numerical value to the time points and the truth value to the Boolean variable, and you consider only the constraints that remains true, all constraints involving the components of the trace are satisfied. So that is basically significant, and that is our goal, mining a significant temporal network. So to to achieve this result, we developed an algorithm which is a miner, and it was interesting because the other implicit and a bit hidden challenge was that of doing that without using any kind of machine learning or any kind of learning at all. And we developed an algorithm. And so if we mine a temporal network from a set of traces, it would be significant for each of the traces. So we don't have so the percentage of traces that satisfy the network. So each trace will satisfy the constraints for the parts that it speaks, let's say. So these algorithms takes each trace in the set and process each statement. Whenever it processes a statement, it basically either add constraints if they are not already present, or it weakens them in order to maintain significance. By weakening, we mean that we keep the most general one, and I'm gonna show you in a minute. So take, for example, this trace. So these are basically the statements that it consists of. So to mine a network, we take the first one and we add a time point. After that, what we do if constraints and time points are not present, we add the time point and we rigidly connect from the first time point from Z. So we assume that there is always a starting point Z for the moment. We rigidly connect it with a pair of constraints whose numerical value is the absolute time point, and whose conditions are the collection of all the conditions that we have either observed or decided before. And you can see that here we still don't know that this is an observation time point. We find out immediately after, because we see that there is an uncontrollable Boolean connected to it. So we turn it to an observation time point and so on, and we basically construct this network. After that, whenever we find a contingent time point, we fix at the moment here an uncontrollable duration, which for the first time is not really uncontrollable because it's fixed to an interval which is a single point. But with the weakening rules, it will be extended accordingly. So basically, we have two classes of rules, and the algorithms process each statement by applying this rule until he's done with the trace and this set of trace. Whenever we process a temporal constraint, so whenever we find a controllable time point that has been executed at some specific time, we add the pair of constraints as I just shown you before. Suppose that we add the constraint in this direction, so we add a deadline. What we do to keep the most general constraint is that as a first thing, we reason on the label. So we take the relevant fragment in the temporal network that speaks for these two time points, and we consider basically two cases. Either the label is a superset also equal of some labels that are already present, or it is a proper subset, so it is a strict subset. To keep the most general constraint, we basically keep the smallest subset, and we keep the maximum numerical value. In this case, significance is maintained. If you take this example, here we maintain these two constraints, which are labeled by A and B, and we raise this number to 7 because it's a value which is greater than 3, and we keep this number because it is already greater than 7. So this constraint still holds here. The other case, so here we just modify the numerical part. In this case, we throw away a set of constraints if this label is a subset of this one. And in this case, we throw away this constraint, and between -7, -8, and -3, we keep the maximum value, which is -3. So this is a delay. So it means that C must be executed at least 3 after Z whenever B holds. And this satisfies also this constraint and this constraint. The third rule is the one that I showed you before. It basically adds a constraint if it does not exist in the network. For contingent links, we do pretty much the same, but with the difference that we either lower the lower bound of the link or raise the upper bound of the link, depending on the corresponding relative temporal distance between the activation time point and the contingent time point. In this case, for example, suppose that in the trace that we are processing this relative distance is 1. We currently have a lower bound of 2, we lower to 1, we extend so that this duration might exist from now on, and the same way we basically keep. If the duration is 8 here, we raise the upper bound of this contingent link on. And you can notice that by since we have a strong monotonicity, we still have that all other constraints and the previous durations are included in this update. So the other rule is that add a contingent link whenever there is no presence. So it's a simple case. So the complexity of this algorithm basically takes into consideration 2 factors: the cardinality of set of traces, which is an asymptotic bound elevated to the power of 2, multiplied by a factor k, which is the size where of the biggest trace in this set, where the size of the trace is basically just the number of statements that appears in it. And in conclusions, we tried to address a mining problem for the temporal network context, and this led us to define significance for temporal network model as a first step. After that, we provided an algorithm to mine a significant STNUs, which was our reference model, and we proved that the algorithm runs in polynomial time. So this is a first step. Future work will address the direction in which we will try to understand if we can mine controllable temporal networks, because at the moment we strongly doubt that what outputs the algorithm might have some controllability guarantee. So that's all.
Okay, thank you very much, Matteo. So do we have any questions from the audience? We're slightly over the time anyway, but maybe we have a few questions. One quick question. What do you mean with a more controllable temporal network? What do you understand as controllable?
One of the problems is that whenever you start from a trace, from a set of log traces, your goal is that of reconstructing some model. In the business process community is that of constructing a business process. Here is that of reconstructing or building a model which means something for that set of traces. And here we considered that in these traces, we explicitly marked the components that appear in these traces as either controllable or uncontrollable. So whenever you have some part which is out of control, you deal with a controllability problem. So you know that if you reconstruct this model has to face uncertainty at some point. And what would be good is that would be that of mining a network which once mined is also controllable for that process. So because if you start with a set of traces and then you can reconstruct the model, you have guarantees of controllability. So from today, we know how we will execute them no matter what will happen. And this is quite difficult because constraints might be incoherent with each other in the traces, or the traces might be partial. So there is missing information in the traces, so we cannot invent it, we cannot predict it. And this gives some slightly guarantees for the type of significance that we define, but still we don't think that as is gives any guarantees about the controllability, because if the traces do not give me any information for some particular scenario which is missing in the set of traces, I basically don't know what to do with that scenario.
Okay. So you mean more uncertainty, more vagueness in the matching in principle. Okay, if there are no more questions, I think we can close the session. Thank you again for